All right, in this video, we'll try example 3.4.1. We're going to try to solve our first system of linear equations. What I'll use is this proposition here that gave us a solution for one simple differential equation. All right, so I'm going to look at this differential system. I have y1 prime is 5y1, y2 prime is 3y2, y3 prime is minus 6y3, and I want to find functions 1, y1, y2, y3 for which all of these are true. So first, write the system in matrix form as y prime equals a y. All right, so I'm going to take y to be y1, y2, y3, and so y prime will be the set of all derivatives. If I assume that these are solutions to this system of equation, then y1 would be 5, y1 prime would be 5y1, y2 prime would be 3y2, and y3 prime would be minus 6y3. Okay, and I want to write this as a matrix times y, so let's see. For the first column, I need just 5 times y1, so that's going to be 5 times y1, 0 times y2, 0 times y3. I'm going to have 0 times y1, 3 times y2, 0 times y3 for the second row, and the third one is going to be 0, 0, and minus 6y3. All right, so this is my matrix A. Notice that this matrix A is diagonal, so that's going to make our life much easier. Let's see how. Right, I'm going to find the general solution for this linear system of differential equation. All right, so let's look at the first equation. I have y1 prime equals 5y1. That's the only one that involves y1. And so I can use the proposition we just saw. So proposition 3.1.4, 3.4.1. So it's exactly this shape. And so my solution will look like this, where A is 5. Second equation, that's the only one that contains y2, and it tells me that y2 should be 3y2. And so the same proposition gives me the general solution for this one. It should be a constant. It could be a different constant, so I'm going to label them differently. I'm going to label C1 and C2 here, and then e to the 3t. And finally, y3 prime is minus 6y3. That means y3 of t is c3 e to the minus 6t. All right, so I have y1, y2, y3, and so I have my general solution. So general solution would be y1, y2, y3. You can place it in vector form. It's c1 e to the 5t, c2 e to the 3t, c3 e to the minus 6t. All right, so notice that part of the reason we were able to solve it using just a proposition is the fact that the y1s, y2s, y3s are not mixed. Each have a single equation and do not appear in any of the other ones. All right, so now I want to find a particular solution with y of 0 is 2 minus 1, 3. So let's see what y of 0 gives us. It's going to be c1 e of 0, c2 e of 0, c3 e of 0. So I'm going to get c1, c2, c3. And we want that to be 2 minus 1, 3. And so I'm going to need c1 equals 2, c2 equals minus 1, c3 equals 3. And so y of t would be 2e to the 5t minus e to the 3t, 3e to the minus 6t. All right, so in this last example, the matrix A was diagonal. In that case, the proposition is enough to solve for y. For a general matrix, we'll first diagonalize A to land in this simpler case. Right, so at this point, we can handle diagonal matrices in these systems, but using what we've done in the last section, diagonalization, and this simpler solution for diagonal matrix, we'll be able to solve these kinds of problems for any diagonalizable matrices.